talk about cutoff for geodesic path on hyperbolic manifolds. Thank you, Charles.
Thank you for the introduction, Hubert. So, and Milton for the invitation. So I will talk today about joint work with Joffrey Mathien, with a PhD student who will soon complete his PhD. And what I'm going to talk about, most of it is on archive. You can see the reference. Okay. So I chose this topic because this is related to a work we did many years, some years ago now with Hubert. Okay, so this will be about the cutoff phenomenon. Okay, so most of you know what it is, but I will recap what it is. So in a language that will be suited for what's going to happen. So you have a sequence of spaces. Okay, so I should try to do that. Okay, so you have a sequence of spaces, okay, which are equipped with a measure, a probability measure, pi delta, which you think of as your equilibrium measure. And on this probability space, you are given for yourself a process xt delta, indexed by delta. So delta is a measure of the size of your, for example, will be a measure of something. Okay, typically it would be, for example, the measure of the volume of your space. Okay, and so you call mu t delta the law of this your process at time t. Okay, and so you start your process at time 0, and its law is mu 0 delta. Okay, so the key assumption is that you want that your initial at time 0, you are very far from your equilibrium state. Okay, so you assume that your measure, equilibrium, your starting measure mu 0 delta, is as far as possible as from the invariant measure. Okay, so you assume that mu 0 delta, the total variation distance between mu 0 and delta and pi delta goes to 0 as delta goes to 1 as delta goes to 0. Whereas the total variation distance is the total variation distance. So it's 1/2, for example, the L1 distance of the density of measures. Okay. And this is, we could consider, of course, other distance, but this one is the traditional one when dealing with a cutoff phenomenon, okay? And I didn't write it, but you will be in situation where for any delta positive, say, if you look at the distance that the law of your process at time t, converge in total variation distance toward your equilibrium distance for any as the time goes to infinity, okay? So this would be another assumption. And then you will say that your measure exhibit cutoff. Okay, so it's a sequence of measure. If or your process xt delta exhibit cutoff at a time which would be a sequence indexed by delta. If when you are slightly below this time, so if you take any epsilon, you are slightly below this time, and you look at the minimal distance you are from equilibrium just before this time t star, and this should go to 1 as delta goes to 0. And but when you are slightly above, this goes to 0 as delta goes to 0. So you have seen many times probably this Heaviside function, which describes this cutoff phenomenon. Okay, and there are refinements where you try to measure what is called the window, which is the amount of time needed to go from 1 to 0 when you are around the equilibrium time. Okay, so this has been vastly explored in many directions in the world of Markov chains. The first example are due to Diaconis and Sheshani in Karl shuffling. And since 44 years now from Cutoff, there have been papers on examples of Markov chains exhibiting Cutoff. Okay. I will give you one toy example, which will be closer to the setting that I want to talk about today, which is simpler from what people are usually considering when they think about cutoff. Okay. So I will consider a cutoff where, so in the cutoff definition, there are two things. There are two things indexed by delta. There is the probability, the state space, x delta, and the initial condition. I will be interested today mostly about cases where the probability space is fixed. Okay. Only the initial condition will depend on delta. And this is especially relevant when you consider ergodic dynamical system. So here is an example. You consider a map, a very simple map, which just moves, which is on the unit sphere. Okay, on the circle, which to x maps to x. Okay. So you equip this space, so assume that the length of the circle is of length 1. You equip it with the Lebesgue measure. So the Lebesgue measure on this circle, and the Lebesgue measure is invariant by this map, right? And now what you consider as, so the state, so there is no delta now, but now where your delta appears is that you consider as initial condition a uniform law on a point around delta, around a point x in an interval delta. Okay, so you can consider a uniform distribution on x between x minus delta over 2, x plus delta over 2. So it's better to look at the picture. Okay, so now if I apply, so this is my this is a uniform measure at the beginning. Okay, so I take a uniform law on this interval. And now when I apply this map once, I will get a uniform law on a new interval, which will be of length 2 delta, now centered at 2x. Okay. So, and more generally, if you apply your map t times, okay, so you will circle around the circle many times when t is large, but at time t, this will be your law mu t delta will be a uniform law on an interval of length delta times 2 to the t, because every time your interval is doubled, provided that the length, that delta to the 2 to the t is less than the total length of my interval, which I have set to be 1. Okay, and the consequence of that is that the distance in total variation between mu t delta and pi, my Lebesgue measure, is 1 minus delta 2 to the t if delta 2 to the t is less than 1. Okay. Okay, so you get an exact formula, which, if you assume, for example, that I will make a stupid assumption that delta is of the form 2 to the k for some k, then after time, when you reach time k, you have your uniform, you have exactly recovered the invariant measure. Okay, so this is the exact formula for the total variation around all times. Okay, so you have a cutoff at time k, which is log of 1 over delta over log 2. And so beyond this time, this is exactly 0, the total variation distance.
Yeah, sorry, I
Yes.
think you mean delta EB 2 to the minus k, right?
Delta, oh yes, thank you. Thank you. And then, but before that, it's given by this formula, but it's very close to 1, except when it becomes very close to k, and the window in this case is just of order 1. Okay, so this is a picture. So I should have written it like that. Okay. So this is a picture when delta is exactly 2 power minus k, but if delta is not of this form, it's easy to recover the cutoff exactly at this time, log of 1 over delta over log 2. So you see, it's a very easy example of cutoff, and it hints at the possibility that for many ergodic dynamical systems, okay, such as this one, with a Lebesgue measure as invariant measure, so on the unit circle or on a torus, or for example, you expect that when you start at an initial condition, which is locally which is very localized. So here, this was my uniform measure on a ball of radius delta. You expect that you will have cutoff generically. Okay, so I have some ongoing work on that, but today I want to speak something in this framework, not for dynamical systems, but for geodesic paths on manifolds, which I will define now. But this will be exactly the same idea. Okay, so what is so I would consider hyperbolic manifolds. So if you are not too familiar with that, I think it will be okay. So you consider M will be an hyperbolic connected oriented compact manifold of dimension D. So which I will usually summarize in terms of hyperbolic compact manifold. Okay, so what does it mean? It means that it is a Riemannian manifold of sectional curvature which is constant, equal to -1. Okay, and this manifold is covered by the hyperbolic plane of dimension D. Okay, so there are various equivalent definition of the hyperbolic space, but one of them is a half space model, for example, where it's H in dimension D. The state is R to the D-1 cross R plus. Okay, the Riemannian metric is given by this formula, and the volume measure, or the Lebesgue measure, the hyperbolic volume measure, is this one. Okay, and so the geodesics in this space are of two types: either they are circular, semicircular, or they are infinite vertical lines. Okay, and the good way, at least for this talk, to think about my hyperbolic manifold, it is that this is a quotient of the hyperbolic space of dimension D by some subgroup of isometries of HD, which are called Möbius groups. Okay, so the picture that you should have in mind, so my picture will be wrong, but okay, it's fine. So, but there will be a fundamental domain, okay, of my group gamma. Okay, so there will be a fundamental domain here, which I can identify with my provided that I can glue together the boundaries of my fundamental domains in a proper way. I can identify my manifold as my fundamental domain glued along the sides, along the geodesic sides of my domain. Okay, and it comes with a tiling, meaning that this fundamental domain. Maybe I should change color. Sorry, I'm very bad at pictures, but it comes with it defines, in fact, a tiling of the hyperbolic space. Okay, so, and each of these domains are isometric, and they are in some sense a copy of them. Okay, so maybe I should have also pictured a manifold. Okay, so for example, in dimension 2, it's a surface. Okay, and then in this case, here you have a genus 2 manifold surface. And what's going to be a fundamental domain? It will be an hyperbolic 8 octagons. Okay, something like that. Okay, but in general dimension and for large genus, it can be pretty nasty to describe the fundamental domain. But this will be the proper way to define it. And this measure, this hyperbolic manifold is equipped with a volume form, okay, which, since my space is compact, the volume is finite. And the volume is the image, if you want. So is the image of my hyperbolic Lebesgue measure to this manifold. Okay, and since it's finite, you can define a probability measure. You can equip your manifold with a probability measure, which will be the normalized volume form. Okay. And now the probability space that I will be considering is my manifold equipped with its volume measure, which is a probability measure. Okay. Now to define you the kind of process that we will consider geodesic path. Okay. So to define properly the geodesic path, you need to when you have your manifold, so you around each point in your manifold. Okay, so maybe this is my manifold. You have a tangent space, which we call the Tx of M. Okay, and the tangent. This is a tangent space at X, and there is something which is called the tangent bundle, which is a disjoint union over all points of your tangent space, of all points of your manifold, of these tangent spaces. Okay, so since I'm considering manifolds of dimension D, you can think of surface. My tangent space are of dimension D. Okay, and this huge collection of so this is called a tangent bundle. And we will consider a unit tangent bundle. So what does it mean? It is that we consider vectors, which are vectors in T of X of M, vectors F in T of X of M, which are of Euclidean norm 1. Okay? And now, when there is an invariant measure, which is called the Liouville measure, which you can write, which lives on the unit tangent bundle, which you can write as the volume measure. So this is an element of M. So this is in M, and this is in T1X of M. Okay, but you can write as like that. This is a volume measure on the manifold, and this is a uniform measure. So it's a random direction, if you want, uniformly random point on the sphere of dimension D minus 1, a uniform measure on T1X. Okay. This is called the Liouville measure. Okay, and now you can define the geodesic flow, okay, which is you start from a point X, okay, so you start from a point X, and you are given a direction V in your tangent in your tangent vector space, tangent space at X. And then what you do is you follow the flow during a time t. So it moves at unit speed, and at any time, this geodesic flow. So it's a point xt, maybe vt, where xt is a point on my manifold, and vt is a point in the unit tangent bundle at xt. Okay. So this is a trajectory. You can think of that as a billiard if you want, and at any time you launch your ball of billiard in your billiard, and at any time it moves at unit speed, and at any time you have a position on your billiard and a direction. Okay, and the geodesic flow is left invariant by the Liouville measure. Okay, and so. What we will do, we will consider an initial condition. So we will take Z0, which will depend on delta, okay, which will be of the form X0 delta and V0 delta, okay, where X0 delta is uniform on a ball of radius X0 and delta, Okay, so as in my toy example of my interval, I have a center x0, and I take my initial position is slightly random. Okay, and x0 is a point in M, and my initial direction will not depend on delta. It will be simply a uniform on T1 x0 delta. Okay, is the process clear? So maybe I should enlarge my maybe. Okay, so you have I have some uncertainty, so I have my point maybe out of color. Okay, so this was yes?
Just a question. Would it be also possible to consider some uncertainty on the direction? Say like
yes,
you pick a direction, you take a small ball. Would it change?
Yeah, it's an excellent question. So if the distribution at the beginning is not too far from uniform, it would be fine. But what would be very nice, but our results are not working in this setting, is also to take something which is, so my initial condition is localized on the manifold, but not localized in the unit tangent bundle. So what would be very nice is to have something localized also on the unit tangent bundle. But our proof doesn't work. For the result, I still have to write.
Okay.
But it's an excellent question. Okay, so so the Liouville measure. So okay, and so but the flow is revertible. Is the geodesic flow? You can just reverse it. Okay, so if you look at the distribution between ZT, maybe delta. Okay, so this is a random variable, this is a low, but okay, I think it's fine. So between the total variation distance between the low of ZT and my Liouville measure is left unchanged by my geodesic flow, because the geodesic flow you can revert it. You go just backward in time. Okay, so this is essentially 1 minus the volume of the ball of radius x0 and delta. Okay, so there is no cutoff here. So you have to observe some cutoff. So we started from that. You have to remove some information. Okay, so what we proved with this is our first result with Joffrey, is that if you only consider the position, then you have cutoff. So as delta goes to 0, maybe I should have, for almost all x0, we cannot prove, so there is an initial condition here. So you take a ball around x0 and x0 is not, we cannot prove that our result is true for all starting point, but almost all, it's fine. For almost all x0, xt delta as cutoff at time log t star, which is log of 1 over delta divided by d minus 1. Okay, so this is our first result. So this is exactly a theorem in the spirit of what I've in my trivial example. So the state space is fixed. It's a fixed manifold, a hyperbolic manifold. But what I am doing is I am taking an initial condition, which is a very, very picked. Okay, so we have other results in our paper which are closer to what people have considered previously, which are what's happening if instead of taking a more and more localized initial condition, I consider a sequence of manifolds of increasing volume. Okay, so to state this result, I need to introduce the Laplace. Yes.
Can I interrupt you for a question?
Sure, many times.
Do you have any idea of what happened to the hypothetical small set of x0 for which this is not true? Like any estimate on worst case scenarios or? Is it something technical, or do you believe that do these things exist, like these exceptional x0s?
I don't think they exist.
Okay.
I think it's an artifact of the proof, but
okay.
Yeah. But this is mostly a belief. I mean, they could be, for example, they could be some part of your manifold which are very pinched. Okay, where you would have a kind of you'll have a geodesic of very, very small lengths, but then you will, when you take, even if you start from one of these very bad points, you will leave them pretty fast. So since the cutoff time is like log over 1 over delta, you should not see them. So I think it's an artifact. Okay.
Okay.
Okay, so for the other results, I need to, and for the proof of trying to explain you the kind of proof that hidden behind theorem 1, I will give you, I need to introduce the Laplace-Beltrami operator, so which is an operator, so it's usually denoted by delta, sorry. So this is a Laplace-Beltrami operator. And this operator acts on L2 of my surface equipped with my probability measure. It is self-adjoint, and it is more than that, it's non-negative. Okay, I will not write you the definition of the Laplacian in terms of coordinates because it's not very informative. So since it's a probability seminar, maybe what I can tell you is that 1/2, the way I normalize it, is that 1/2 of the Laplacian is the infinitesimal generator of my Laplacian, or the usual one, infinitesimal generator of the Brownian motion, bt on n. Okay, so this is the generator of the Brownian motion. Okay, so since I assume that my manifold is compact, the spectrum is discrete, and since my manifold is connected, there is a single eigenvalue which is equal to 0, which is associated to constant vectors, and all other ones, they are strictly positive. Okay, I can increase them in non-negative, in a non-decreasing sequence, and Vailo tell me that lambda k grows like a constant, which you can read on Wikipedia, for example, times k power 2 over d. This is called Weil's law. Okay, so exactly as the cutoff time, which was our cutoff time, just depended on the dimension. So it did not depend on a very subtle invariant of the manifold. Okay, but the Weil's law is also universal. So the way the eigenvalues grows just depend on the dimension of your hyperbolic manifold. Okay, you can also define your Laplace-Beltrami operator directly on L2 of my hyperbolic space, equipped with what I denoted by my Lebesgue measure, hyperbolic measure L. It will also be self-adjoint positive, and then the spectrum this time there is lambda 0, which is the spectrum, sorry, is strictly positive now, and the spectrum of the Laplacian operator on HT is an half interval, which is d minus 1 over 2 squared plus infinity. Okay, and I will denote in the rest this number sigma d. Okay, and there is something which is called Alon-Bopana bound, which says that if you consider a manifold of large volume, okay, its first non-trivial eigenvalue, which is lambda 1. So maybe I should write it in lambda 1, this one. Lambda 1 of which depends on the manifold, cannot be arbitrarily large. So which says that lambda 1 of m is bounded by the leftmost point in the spectrum of the Laplace operator of HT, plus some correction terms which depends on the dimension and which goes to 0 as the log of the volume of the manifold. Okay, so this is not very hard to prove, but this is a nice fact. Okay, and it has been a problem, an open problem for many times to prove to find manifolds which reach this upper bound. Okay, and it was first proved by Maggie and Hyde that there exist hyperbolic surfaces, so in dimension 2. There exists a sequence Mn with volume of Mn going to infinity. So by the Cauchy-Binet, it's 2 pi. For surfaces, the volume is simply 2 pi times g n, the genus. Okay, let's skip that. Okay, so there exists a sequence of hyperbolic surfaces of volume going to infinity, such that lambda 1 of them is equal to sigma d plus little o of 1. Okay. And then there have been more proofs, one by Anantaraman, still in dimension 2, Anantaraman and Monk, and very recently by Van Andel, Puder, and Maggie. I should have put Maggie. So all these papers they are from 2024. So this was 2023. Proving, they have given random construction of hyperbolic surfaces, still in dimension 2, which satisfies this part. Okay. So okay. So our second theorem is very closely related to. It's related to what people have done on graphs. So now you take delta to be fixed. Okay, so I remember my initial condition is on a ball of radius delta, but now I assume that I have a sequence of manifolds of volume which goes to infinity, and I will call Vn the volume. And I assume that they have an optimal spectral gap. Okay, so they match the Allen-Bopanov bound. So in particular, there are no known examples in dimension 3 or higher of this theorem. Okay, but let's keep that. Then, if okay, so we have at any point there is something which is so you take initial condition which I will done xn, and you look at locally you have your manifold M, and locally it is isometric. It is locally isometric to HD. Okay, and there is something which is called the spectral radius, the injectivity radius. Sorry. Which is the largest radius in your manifold, such that the ball of radius around x of radius rho of x is isometric to the hyperbolic plane. Okay, so if your injectivity radius is not too small, then your process xtn, so it's indexed by n now, has cutoff at time t star n, which is log of Vn divided by d minus 1. And if you consider also, this is true for, and this is also true for the Brownian motion, you take the hyperbolic Brownian motion, and the time is 2 times log Vn. Okay. So there were previous results by Golubev and Kamber, which I will write, which were for specific case in the case of dimension 2 and for the Brownian motion. Okay, so for Golubev and Kamber in 2019, they consider d equal to 2 and the Brownian motion and a subset of, okay. And this is, there is an analog result for graphs, for regular graphs, there is an analog result, which is due to Perez, Lubetsky, and Perez in 2019. And this paper has inspired the paper of Golubev and Kamber and has inspired our proof. Okay, so as I told you, this condition to be spectrally optimal is extremely demanding. So we have a relaxation of that, which is called the Sarnak-Chu density condition, which I will define for you. So this is called the Sarnak-Chu density condition. Okay, so what is that? It is, you define for S in 0, 1, you define I of S, which is the limit as n goes to infinity, so it's a lim sup, of the law of the, you look at the growth rate of the number of eigenvalues of your manifold, which are below the interval 0 sigma d. Okay, so you count the number of eigenvalues of your manifold Mn, which are less than sigma d, which was times 1 minus s. And you divide by the log of the volume, which I denoted by Vn. Okay, so you call that I of S. And the Sarnak-Chu condition is saying that Sarnak-Chu, this is saying that for all S, I of S is less than 1 minus S. So this condition appeared in some exchanges between Sarnak and Chu. And there are examples of manifolds which satisfy the Sarnak-Chu condition. It's easier to prove. At least in dimension 2, there are some classical one, but in dimension higher, I don't know, honestly. I'm not enough of a geometer to tell you. Okay, and so we have the analog of the theorem 2 under the assumption that but if you have the Sarnak-Chu condition, if you have that you have a spectral gap, meaning that the lim of your lambda 1 is positive, then for almost all points, okay, so you can be more precise, but for almost all points, the conclusion of theorem 2 holds. Okay, it's not very precise way to state it. But...
So a question about theorem 2.
Yes.
So this condition delta positive, it's really natural when you consider xt because you cannot have result when delta is equal to 0. But for Brownian motion, can you choose delta equal to 0 in your result or not?
Delta yes. For the Brownian motion, yeah, you can delta can be equal to 0.
Okay.
Yeah, it's just that we focus more on the geodesic path, but yeah, it's a good point. Okay, so and this result is related to a paper with Hubert that we did a few years ago, where we prove an analog of this statement for regular graphs. Okay, so I will give you some ideas of proof in the time that remains. Okay, so so as I said, the paper that has started this kind of spectral techniques for proving cutoff is this paper by Lubetsky and Perez. Okay, so this is a spectral strategy that has been used for Ramanujan graph, so graph with the largest possible spectral gap. Okay, so how does it work? first, I will give you the lower bound because the lower bound is very easy. Okay. So in the cutoff, you have two conditions. So you have to prove that before cutoff time, you are far from equilibrium, and slightly above cutoff time, you are at equilibrium essentially. Okay. So how does the lower bound work? So this is elementary. Okay. So you have to remember that my picture that you can think of M as being one copy of here, and then there is a maybe I should change color every time, but there is a tessellation of there is a tiling of the hyperbolic plane with copies of M of my manifold. Okay. Okay, so there is a covering map, which okay, so there is a covering map which goes from HD to my manifold M, okay, and this is essentially a picture of my covering map, and which sends, for example, a given point of my manifold E, which is 1, 0, 0, 0, 0, if I use a half-plane space, to my initial point X in my manifold, okay, of finite volume. Okay, so if you have to know that if you are in HD, so maybe I can erase that now. Okay, if you look at the ball of a radius T, the ball of radius of center E and radius T, it's a Euclidean ball also, but not centered at E, but whatever. And the radius, maybe I should denote it by R. Okay, so T, sorry. Okay, and the volume of this ball, the volume of the ball of radius T in the Euclidean space is exponential. Oh, it's equivalent to, it's a sinh, but okay, it's essentially the exponential of d minus 1t. Okay, so this is the volume in the Euclidean space, in the hyperbolic space. Okay, so now if I look at the push forward of my measure, so this is my measure with reduced delta, my uniform law with measure delta. When I push it by my process, by my geodesic path, okay, I will get something like a measure which will be supported on an annulus of width delta. Okay, so the volume of my annulus is of order delta times exponential d minus 1t. Okay, and since to have cutoff, you need to have the volume. So the volume of so you have the density. Maybe I will call the volume of the support of F. So this is the volume on my manifold on M. Okay, it will be less than the volume on HD of my annulus, in my green annulus, which is essentially delta exponential d minus 1t. Okay, so if delta exponential d minus 1t is much smaller than 1, so in particular, then you cannot have cutoff. Because the distance, maybe I should have written it this way, the distance in total variation between, sorry, Ft, I should write, sorry. Ft is a density. It's, I have my measure, maybe I can write a delta, started at X, okay, and I take the density with respect to my equilibrium measure. Okay, so maybe sometimes I will write a dependency in delta and X. Okay, so the total variation distance between mu t delta x and pi delta, pi does not depend on delta, sorry, is at least 1 minus the volume of the support, which is delta times exponential d minus 1t. Okay, so if the delta exponential d minus 1t is less than 1, then the distance in total variation is close to 1. Okay, so this gives this is essentially the idea of the lower bound. So it doesn't depend on. So this is I gave you the. Maybe I should have written the volume of times the volume of m. Okay, I should have renormalized by the volume of m. Okay, so when the volume of m goes to infinity and delta is fixed, you get the same, the lower bound that I've claimed. Okay, so the lower bound is not super hard to get. The upper bound is based on the following miracle, and this will answer the first question of Uber. Why did we choose a uniform distribution on the unit tangent space? Okay, so you can write, so Ft is the density at times t with respect to my equilibrium measure of the law of my process, right? So Ft it's the image by some operator of the density at time 0, and this operator is called the spherical mean operator. Okay, and it acts like that. Ft of f, so it lives in L2 of m pi. Okay, and At of fx is the integral over T1x of m of f of gamma t of xv d sigma xv, where d sigma v is the uniform measure on the unit tangent bundle at tangent space at x. Okay, so there is an explicit expression for this operator, which describes me how the density moves with time. Okay, and there is something which is called Delsart formula, which is two facts that delta, the Laplacian, and a of t, they commute. Okay, so since they commute, they have, if they were matrices, they should have a common orthogonal basis of eigenvectors. And so delta as a, so I should have said that earlier, but so delta as a complete orthonormal basis, which I could write like that, okay, where phi k is a complete orthonormal basis in L2 of m pi. Okay, and a of t, you can write it as a sum of mu t lambda k phi k star. Okay, and nu t lambda is some function. Okay, it's some function from r plus to r, which tells you how an eigenvalue, an eigenmode, an eigenfunction with eigenvalue lambda is transformed by this spherical mean operator. Okay, and with Joffrey, so the Delsart formula gives you an expression for nu t lambda as an integral of order as an integral of in dimension d. Okay, so we have a lemma or a proposition which computes. We have an explicit formula for this function. We know that nu t lambda is some explicit constant which depends only on d of some cosine plus x, some sinh of I u minus d minus 1 over 2, 1 minus x squared, d minus 3 over 2 dx. So this is an integral over the interval, where CD is some constant, and here I have written lambda as sigma d plus u squared. Okay, so where u is either positive number or a complex, purely imaginary point. Okay, so there is an explicit formula for the eigenvalues for this map, which, okay, in particular, for example, in dimension 3, you could write that nu t lambda is exactly the sine of ut divided by 2u sine of hyperbolic of t, sinh. Okay, so maybe there is a constant, and it's a 2, sorry. So we have an explicit formula in even dimension, in odd dimensions. Okay, so in particular, the way you have to think about this function, so it's 1 at 0, it's 1 because it's a Markov operator, and then it has some oscillatory behavior. And the corollary is that we know how they behave. That if lambda is larger than is less than sigma d, we know that nu t lambda is bounded by t. Okay, maybe I will be. It has some decay of this form. Okay, if you play with this formula, you have singularity point. Okay, I spare you that. And oh, sorry, plus t times imaginary part of u. And if lambda is larger than sigma d, nu t lambda is bounded by t times something like 1 over u power d minus 1 times the same exponential decay. Okay, so we have a way to bound the absolute value from the explicit formula to bound the way the eigenvalues of the Laplacian are transformed by this spherical mean operator. Okay, and now I can give you in 5 minutes remaining, I can give you the proof at least of the theorem for the optimal surfaces. This is a simpler. Okay. So all this is essentially this Perez-Lubetsky proof now. It is that you are interested by the total variation distance between mu t and pi. Okay. So mu t depends on x and delta. Okay. But okay, so you write it as 1/2 of the density with respect to pi. Okay. And what you do is maybe I will do, okay, so the proof of theorem 2 will be easy. You apply a Cauchy-Schwarz inequality. Okay, so you forget about that, don't care. It's less than the integral, so maybe I will put a square here. The square is here. So it's less than, you can put the square inside. Okay, but now maybe I should write with what I'm integrating on. Okay, with ft of y minus 1 dpy. But now we know that ft of y is at of f0 of y. This can be written as the sum over the eigenvalues of the Laplacian of my map nu t lambda k of f0 phi k star phi k of y. Okay, and since the phi k are orthonormal, you can use Pythagoras theorem, which tells you that this guy, this integral is exactly equal to O. You use that nu t of 0 is 1, and that phi 0 is just a constant function. So the minus 1 just kills the first eigenmode, and you get the sum over all k larger than 1 of nu T lambda k squared, maybe I can write it like that, times the integral of f0 scalar phi k squared dpy. No, yes, there is no dpy. What did it happen? No, okay. Okay. And now you can deduce, if you are in the setting of theorem 2, in this sum, so in theorem 2, you are saying that lambda 1, is, let's say, larger than sigma d minus little o of 1. So our corollary tells us that nu t of lambda k, they are all bounded by exponential t times d minus 1 over 2 plus, let's say, little o of t. Okay, so you get from your expression that the total variation squared between mu t and pi, it's bounded by exponential minus t times d minus 1 plus little o of t times the sum of the squares of f0 against. Okay, but now you can recognize this is certainly less than the L2 norm of f0, which, if you make the computation correct, is of order delta minus d over the volume of M. Okay. And now you deduce that you will have, if volume of Mn goes to infinity, you will have delta is fixed. You will have this distance will go to 0. Sorry. This as t goes to infinity. Oh no, it will be a little o of 1 if t is much larger than 1 over d minus 1 times log of volume, which I called. Okay. Okay, so this is the essence of the proof of theorem 2. It's very easy. So you can do a refinement for theorem 3, which was with Sarnak-Xu initial condition. I think my time is over. So and for theorem 1, it's more subtle because this is too small. Okay, you cannot get, this is too small, and you do not get this is too large. Sorry, you do not get the proof of theorem 1. You have to use the extra information for theorem 1, which is more interesting to prove, which was the one for the fixed manifold. For theorem 1, you have to divide this sum, which was it? This sum, okay? Instead of bounding, you have to, this was the proper expression. Okay, this expression, you divide this sum for given values of k, and you will use the fact that nu t of lambda, you really need to use that nu t of lambda dk like lambda power, I forgot, d minus 1 exponential times d minus 1 when lambda is large over 2. You really need to use that, plus you use the Weiss law, which tells you how the eigenvalues grow. Okay, so I have to stop here, but essentially this is a spectral argument which is more subtle than this one, but this is the same spirit. Okay, so I think this work beyond the case of geodesic path opens a few directions. For example, we think that as Hubert has suggested, it would be very nice to have something which is also picked, very localized in the unit tangent space. This would be very nice, but our proof do not really work because the spectral theory, the spectral analysis of the spherical operator becomes much more tricky. And beyond that, we are trying to get new examples. There is a kind of large category of dynamical systems where we can prove the cutoff for starting from a localized initial condition. I think that this is a pretty universal characteristic of dynamical, ergodic dynamical system. Okay, thank you for your attention.
Questions? I have a question about this. Is there any way to describe what these optimal surfaces, like these Ramanujan surfaces, look like? So like in these constructions?
Yeah, so the way there is a yes, so there is they look like they are random constructions. So there is an analog of a uniform measure on random regular graphs, which is called the Wien-Petersen measure, which is a measure on the Teichmüller space. But okay, so it's possible to construct. So this is a work of Merzakani and it's possible, and Alan Taraman and Monk. It's possible to compute to really do some explicit probabilistic computation when you integrate random hyperbolic surfaces according to this Wien-Petersen measure. And it's not exactly a Lebesgue measure, but it is as close as you might hope from the Lebesgue measure on the set of hyperbolic surfaces. Okay, and then you have to think of them as their injectivity radius. That the typical injectivity radius is very large. So if they have volume V, the typical injectivity radius will be like a log V. So they look almost as so, and the injectivity radius cannot be much larger than log V because of exponential growth. So they typically they are as close as hyperbolic plane as a hyperbolic surface can be. And
in dimension 2, the genus of the surface, how does it evolve with the volume?
So this is a Gauss-Binet formula, so the volume will be 2 pi times G, if I remember correctly.
Okay. But does it depend on the fact that this is optimal or this is always true?
No, it's always true. The volume cannot be, so my manifolds are very specific because they need to have constant curvature.
Yeah, okay.
So the volume is discrete. It can take only a discrete set. And this is true in dimension 2. In dimension 3, I think it's true, but it's much more complicated. And beyond that, there are very few things which are known. Yeah.
Another, I don't know if it's a question. It's very vague, but this okay, it's because of your picture partially. Your flow X, it really looks like a non-backtracking random walk. So were tools used for non-backtracking random walks useful in here as an analogy, or?
Well, at the beginning, it was an analogy. So I thought that such a spherical mean operator, it should be possible to have an explicit formula for, because geometers, I didn't really care about the explicit value of, what is the explicit value of this function. And so I thought, since I knew that the analog of that in the discrete graph was, you could write an explicit formula, I thought to myself that it should be possible to write down an explicit formula for general hyperbolic manifolds. And so this is the simplest expression that we could get is this one. But so yeah, in dimension 3 or 5, it's you can write it. It's a polynomial of this form, so it's pretty neat. But there are phenomena which do not appear in the discrete setting. This sign and this damping factor is not present in for graphs. And interestingly, this damping factor, which is that it decays like lambda power t minus 1, is precisely what makes the proof work for fixed manifold. But yeah, so but this is one example of a proof. I think for the example we have been working on dynamical ergodic dynamical system, we don't use a spectral approach. So it's not necessary to use spectrum. For this problem, I don't know how to do otherwise, but yeah, maybe there are simpler approach, more elementary or less demanding approach. I don't know.
Okay, well, thank you. Okay, so thank you, Charles, again for this very nice talk.
Thank you. Thank you for the invitation. Have a good afternoon. See you.
Ouais, à plus.
À plus, ciao.